This video is for Griffiths E&M section 2.3.5, talking about boundary conditions. So we have talked about a little bit in previous videos about what happens when you evaluate the potential of a charged sphere or spherical shell as you approach it from infinity and as you go inside. All right. We talked about previous questions had asked about whether or not this potential was continuous or not. But we haven't talked about at all how the electric field behaves as you go from one side of an object to the other. Okay, so let's do that. It's important to note that we're going to take care of two separate, unique scenarios. The first is going to be for a spherical but hollow shell. All right, this is going to be a shell that has a surface charge density, sigma, and a radius r. And this is going to be borrowing the result from problem 2.1.1. And the other that we're going to look at is going to be a solid sphere, so not a shell. Let's say that these are the same size, but it has a volume charge density, rho. This is problem 2.12. Okay. Hopefully you've done it by now, or you will be doing this soon. All right, so if I borrow from those solutions, I know that the electric field inside of my hollow sphere is going to be 0, right? Hopefully you can rationalize that fairly quickly with the fact that Gauss's law says that the charge enclosed is telling you the electric field. If it's a shell and you draw a Gaussian sphere inside of that shell, then you have no electric field because you have no charge enclosed. And then the outside gives you sigma r squared over epsilon naught 1 over little r squared in the r hat direction, where little r is the distance from the center of the sphere to the point that you evaluate the field at, and capital R is the size of your sphere. Okay. Now, we can evaluate what they're, take the previous solutions from the electric field inside of a solid sphere. That is 1 over 3 epsilon naught rho r in the r hat direction. Notice it's no longer 0, and it's not even a constant, right? It depends on where you are inside of that sphere. And then the out is rho over 3 epsilon naught r cubed over r squared in the r hat direction. Now this form may not be exactly the form you get from 2.12, but if it is not, convince yourself that you can get this to be equal to what you have previously. Okay, so now the question is, what happens when we take our position to go to the edge of our sphere, but we have two solutions, one for the inside and one for the outside. So what we're going to do is we're going to take our outside solution and set r equal to r, and we have an inside solution, and we're going to set r equal to r, and we're just going to compare those across each other. Okay, so for the hollow sphere, I'll just keep everything in its own column. All right, E in is still 0, and E out is set little r to big R. That becomes sigma over epsilon naught in the r hat direction. Great. And then for the other case, the solid sphere, we have E in is 1 over 3 epsilon naught rho capital R, r hat, and E out is rho over 3 epsilon naught capital R hat. All right. Hopefully you notice that those two electric fields are the same, while these two electric fields are different. All right. When you have an electric field generated by a surface charge density, so sigma, the one on the left, you have a discontinuity in your electric field. Whereas if you have a solid sphere, solid object, or something with a volume charge density, there is no discontinuity in the electric field. Right, so now you have another tool in the toolbox. Right? If I tell you that you have a particular type of charge density and you approach a surface, you would be able to know what the charge or what the electric field looks like on the other side of that surface. If you know that the surface has a surface or a volume charge density associated with it. In fact, we're going to show later probably that this is always the difference, sigma over epsilon naught. Regardless of the geometry, it has nothing to do with the problem. That's always going to be the difference in the electric field compared to in versus out.